Hi everyone, welcome to MathSpellBook. I'm your host Peter, and we are going to engage with a little bit of rings today with Sascha. So let me just connect with Sascha on Discord and he will begin. So, hey Sascha, we're on stream.
Hey.
The floor is all yours.
Alright. Let me join the Calidra rooms.
How you doing though?
Good.
Cool.
I might start the AC though. Alright. So last time, let's change this real quick. Okay, last time, we did introduce Cauchy sequence.
Yep.
So the definition, I will write it for the rational number. So a Cauchy sequence was something like n is a sequence of rational number. Well, okay, maybe I should change a little bit my wording. A sequence of rational numbers, and is Cauchy if we have for all epsilon greater to 0, there exists some big rank n such that all the rank that go after big n, we have the following inequality that hold. AP minus AQ is less than epsilon. All right. Okay. And the moral of the story was that Cauchy sequences are very well behaved. And we've even shown that convergent sequences are always Cauchy. And I mean, usually, and basically the moral, I mean, at least the intuition we should have about Cauchy sequences, they should usually converge.
Yeah.
If they do not, then it means that the space has some kind of issue. They're like missing points or something. And one cool thing about Cauchy sequence is that, okay, if they don't converge, you can sort of think as, in fact, they converge, but they just converge in a bigger space where you have the missing points. Okay, so Cauchy sequences are kind of able to see the point which are missing, which is very great to define the real numbers, because in the rational we're missing quite a few numbers, like square root of 2 and stuff like that, right?
Right.
So last time I introduced a notation, I introduced a set which I call Cauchy Q, and this was the set of all rational Cauchy sequence. Okay.
Okay.
And last time we showed some properties of this set. First of all, we showed it's a ring. We showed like if I take two Cauchy sequences and I try to add them up, I still get the Cauchy sequence. And I can also make sense of multiply Cauchy sequence. And I mean, last time effort, part of it was spent on showing that this was a ring, at least the part which are a bit more complicated. And basically I said, well, Cauchy sequences are able to see like the missing points.
Okay.
And what we would like is like, I mean, as they're able, so what is cool about Cauchy sequence? So they're able, so they're also able to see every rational numbers. Because, for example, if you want to treat a rational number as a Cauchy sequence, what you can do is you can fix the sequence n is equal to q, where q is some fixed rational number.
Okay.
So you get a sequence which is just constant, which always give you q. Okay. I mean, obviously, if the sequence is constant, then it will converge to q. I mean, there's no problem there. But there was kind of an issue to think about real number as like as Cauchy sequence, is that we get a lot of redundancy, right? Last time I gave an example. If we have the sequence, well, maybe it was not exactly the example I gave, but it will do the same. So let's say it's equal to 1 if n is equal to 0 and 0 otherwise. And let's say you have another sequence which is just n is equal to 0. Then those two sequences are different because, you know, for example, n is equal to 0, the two sequences take different values, right?
Right.
But at the end, they still converge to 0, right? So if we think of Cauchy sequence as number, I mean, those two guys should be the same, right?
Right.
I mean, both of the sequences should represent the same number, which is namely 0. So we're going to have to do something about it. So the something about it will be, we will define R as the set of Cauchy sequence, quotient out by something here, okay, by some equivalence relation. And so I could just introduce this equivalence relation without like just the way we did for like every other number, from going from z to q and so on. But here I want to show that actually when we do this quotient, we actually preserve the arithmetic property of the rational number. Namely, we have a notion of addition and multiplication on this set. So we get a ring, and in fact we will get a field.
What did you write underneath Cauchy? What did you write under the Cauchy? Q.
So this guy will be some kind of equivalence relationship, and that will be like the point to the lecture to define what it is.
What is it? I0? Is it?
Yeah.
Okay. let's see. Aspire has asked a question. Guys, from watching all of this rigor, I have a question about the difference between calculus and real analysis. Does that rigor affect the applications of the field? Do you want to answer this, Sascha? Or, like, do you want me to give my take on it?
So the question is, what's the difference between calculus and real analysis?
Yeah, I think so, because it seems like they're asking, does the rigor affect the application of the field?
So usually calculus is more like on like computation side of analysis, and analysis is more like about having rigorous definition and theorem.
Yeah.
So you get like a real mathematical theory if you want.
Mm-hmm.
But I mean the computation part is also very important, but you need to have both.
Yeah.
And,
so, do you want to continue on?
Yeah, and if we go to what is application of real analysis, well, yeah, there's like stuff that you cannot really define using only you can not really define using only calculus. You need some like more. You need to a little bit more about your object, like a real definition, and that can allow you to work. For example, one example that one will encounter in real analysis, which is not very obvious for people in calculus, is the notion of uniform convergence. And for example, this concept is very important because it allows you to, for example, to study the solution to the heat equations and being able to make sense of convergence of those solutions. I mean, for basic computation, you can like ignore sometimes the theory, but when you do a little bit more advanced stuff and you want to understand it, you still need a real analysis, and that's pretty much it.
Right.
Okay, so now we're gonna move it.
Hold on, Sascha. My stream kind of cut out, so just gonna wait a little bit. Okay.
Yeah,
the stream is reconnecting. Yeah, sorry about that. Yeah, we're like in the red. I'm waiting until it gets into the green.
All right. Okay. Fine.
Hopefully, it gets back to the green soon because it's still in red. But don't worry. I'm also recording. I recorded what you said because I think it cut out when you were like giving your explanation. But okay, I think we're back. Okay, yeah, sorry about that. But to answer your question, Aspire, yeah, what Sascha was saying is that both of them are related. So calculus and real analysis are related. Real analysis actually is the backbone of calculus. So you don't really need all the rigor for calculus, but for real analysis, you have to have all this rigor to explain calculus.
The internet went down something. Can I hear? Oh, now I hear you. Okay.
Yeah. But my streaming is still like cutting out.
Oh no.
Yeah. Come on, connect. I'm recording everything from my computer, so like I probably might have to upload this VOD. Come on, connect. Yeah, sorry about that. Yeah, my internet's not the best. That's the reason why like we keep cutting out.
Yeah.
Okay, now it's reconnecting. Alright. Okay. Yeah, sorry about that, guys. Okay, so we're connected now. Hopefully, Aspire, that answers your question. No, it's okay. That's mainly on our part. Like, basically, like, my internet's not the best. That's the reason why we keep cutting out. But yeah, like, in short, in one sentence, basically, calculus is just more computational, and real analysis is basically a more rigorous way of explaining calculus without mainly numbers. That's basically why it's so rigorous. Hopefully that answers your question. Okay,
All right.
Sascha. Yeah, let's continue.
So,
Okay.
for today's lesson, we're gonna take a step back from what we did in analysis, and we're gonna do some algebra.
Okay.
And basically, so I mean, if you keep in mind that R will be given as a quotient of Cauchy sequence by something, you will see like why the thing I talk about why I talk about algebra today will be relevant to that.
Yeah.
So we're gonna talk about rings. So here I'm gonna assume, so let R be a commutative ring. So commutative just means that multiplication is commutative. Okay.
Okay.
And I will give you some example. For example, R can be a Z, can be Q, can even be a Cauchy sequence. Are you still here?
Yeah.
Okay, there was like no noise, and I was kind of worried that the stream like cut again.
No, I was just writing.
Okay. So example of commutative ring are Z, the rational, Cauchy sequence, and also you have polynomial. So okay, maybe you're not familiar with this notation, but this is the set of all polynomial. And the little q in front of it just means that with the coefficients are rational. With q coefficient.
Yeah, I started reading a little bit about rings before, actually, like when I woke up this morning. I was just so surprised that there are things called semi-groups and groups, and I was like,
yeah.
Oh, there's a lot to it.
Yeah. I mean, usually people care more about like groups and
what's in front
rings?
of the? So when you wrote the set of all polynomial with what's the thing in front of coefficients?
Q, the rational.
Oh, okay.
So basically, an element of this guy will be like 4/2 x squared plus, I don't know, 3/2 x plus 2. So this guy will be inside of the polynomial with rational coefficient because.
And that's just an example you're using with numbers. Right?
Yeah. Because all the coefficients in the polynomial are rational numbers.
Okay.
That's the reason why. Okay, so I mean, I will do it for an abstract commutative ring, so I will not use those examples. I mean, I will give example of the concept using those, but
yeah,
everything will work with a regular commutative ring, so I will not need those specific example, but just keep in mind if you need a concrete example, those are good example. Okay,
yeah.
And now we're gonna introduce something which is gonna be important for ring, which are called ideal. I don't know if you heard of that.
I've heard of ideal as a regular word, but not in mathematical terms.
All right. So we're gonna have a definition. So again, R will always be a commutative ring. Okay. You can do it for non-commutative ring, but you have to. I mean, there's kind of it's kind of a more complicated notion because you have to distinguish between left and right ideal, which is a bit annoying. And I don't really need those, so I will just work with commutative rings, so I don't have to make the distinction. So a subset I of R, so R here is a ring, commutative ring.
Okay.
Is called an ideal of R if we have the following. So what I'm gonna ask is I'm gonna ask that 0 is part of the ideal. Okay. The second property will be that for all x and y which are inside of I, I'm gonna ask that x plus y is also inside of I. Okay, so it's closed under.
So 0 is in I for the first one.
Yeah.
And.
Yeah.
Okay, and x and all y are in the ideal, and x plus y is also in the ideal, right?
Yeah. So
Sounds
this
like a vector space.
Yeah, it really looks like that. And what else we're gonna ask is we're gonna ask that if I have an x inside of I will also ask that the additive inverse minus x is also inside of I.
Okay.
Okay. I mean, here I will not really use this terminology, but this precondition just said that I is an additive subgroup. Okay. So you can if you have an element, you have the neutral element for addition, which is 0, and you can and it's stable under addition, and it's also stable about taking an inverse, additional additive inverse. And the last condition is a bit weird.
Okay.
But you will see when I will. I will show you kind of like the prototype example, like the one example where this definition comes from, and then you will probably understand a little bit better. So the last property is called absorption. So let's say you have an element little r inside of your ring R, and you have a little x inside of I. Okay. Then what you will ask is that r times x is also inside of I. Okay. Sometimes we call this property absorbing. So if we have an element or ideal and we multiply it by anything else in the ring, then we will still get something inside of the ideal. So it's kind of absorbing those elements.
So for R, right? R, like little r in R, right?
Yeah.
Does the little r, can it be in the ideal or it cannot be in the ideal?
It can be.
Oh, okay. So it's versatile, right? So it doesn't have to be like, oh, it cannot be in the ideal for R to be multiplied by X to be in the ideal, right?
Yeah.
Okay.
Yeah, as the definition says, for all elements inside of R.
Okay.
So as big I is a subset of R, of course it holds for those elements as well.
Okay.
And let me give you a list of examples, because right now, this definition seems a bit weird. So there's like one example, which is the trivial one, is you can take I to be R itself, the whole commutative ring.
Yeah.
So obviously this thing will be closed under addition and absorbing multiplicatively, so there's nothing to show there. And the other trivial example is when I is equal to so maybe I should not write like that, is equal to the set that contains only 0.
Oh, okay.
So, the first three properties are kind of trivial because there are only 0 inside of it, so...
Yeah.
Of course, 0 plus 0 is 0, and minus 0 is 0, so...
Yeah.
And the last property also is quite obvious, because if you take x inside of R, and you look at... well, I guess that's something you have to show, but I will assume it. If you multiply something by 0, you still get 0. So those two guys are kind of like the trivial example that works for every ring. Okay.
Yeah.
A more interesting example would be when we work over the integers. Okay.
Okay.
Then I already kind of mentioned that. I don't know if I did on stream or maybe offline to you. But you can have set like that. Usually we call it NZ, and it's basically just all the multiple of n.
And n is supposed to be like a number that's multiplied by
n is inside of z.
Okay.
Yeah. Where x is some kind of integers. Yeah.
So n multiplied by x, and then x is just an element of the integers, right? Okay.
Yeah. So those concretely are just the multiple of n. Okay. So if we take an even more concrete example, we have, like, for example, 2z. Those are the multiple of 2. And you can check the definition quite easily. Let's, for example, do it for the multiple of 2. So if you take two numbers which are multiple of 2 and you add them together, you still get something which is a multiple of 2, right?
Right.
And I mean, the first 3 axioms are quite easy to check, and the last part just said that if you have an even number and you multiply it by any other numbers, you still get an even numbers. So those are kind of the important. Those are kind of the non-trivial example, which are quite interesting to look at.
Okay. So for the examples you show, basically it's like we have an ideal that can equal its ring. So basically the ideal can be just the ring itself. We also have a ideal where it could be the set containing only 0, which means that I'm guessing any operation, addition and multiplication, those 2 operations, if you do anything with 0, it's just gonna end up with 0, right?
Yeah. And also, just as an outside, usually we call this guy, we just call it 0.
Okay.
Just a notation thing.
Okay. So also, so if x is a real number, or x is in the ring, so that's explaining the property of the ideal that basically contains 0 as its set, right?
Yeah.
Okay.
Basically those examples, we can generalize them a bit. Okay. So one way to create ideal is here basically what we did to define those sets is we started with an integers, right?
Yeah.
And we've looked at all the multiple of them. And we can usually do that also for a general ring. So let R be a commutative ring. And let little x be inside of R. Then we can form a ring, an ideal out of this. Okay.
Okay.
So what you will see in textbooks is that they will write something like that. They will write x inside of some parentheses like that.
Okay.
And this guy is a set, which is defined as the following.
Thank you for the raid, Zach. Welcome, raiders. Welcome.
It will be defined as all the multiple of x. Okay.
Okay, so basically, let's see, R. So little r is in the ring, right? And basically, it's multiplied by x. Is x also in the ring, or is it in like a?
Yeah.
Okay.
That's just like one element that we chose at the beginning.
Okay, and then so basically the multiplication of r and x is supposed to be still in the ring, right?
Yeah.
So why? So basically, the reason why we put it in parentheses is to show that it's a commutative ring. Is that the reason why you put parentheses around the x?
It's just a notation. So the way you want to, usually the way people would say is that this is the ideal generated by x.
So the parentheses represents an ideal of x? Is that?
Yeah. So usually the parentheses mean generate by, and then you have the thing in the middle of the parentheses.
Okay.
And one way to think about this kind of idea is just the multiple of x. Okay. So if we go back to the integers, when r is equal to z, then and let's n be some kind of integers, then this notation is just the one that we had earlier, which is just the nz. Okay, they're just like they're exactly the same set.
Okay.
Okay. And we can, maybe I should have stated a little bit more clearly, but this guy is an ideal. And the check is pretty much the same way that we checked that NZ was an ideal. Okay. We can do a little bit more general. Instead of choosing one element, we can choose multiple elements. So let's maybe take a little bit more elements. So let x1, x2, up to maybe xn maybe, the element inside of a ring, then we can generalize this notion to the ideal generated by those guys. Okay.
Okay.
And what will be the definition? Well, we're basically gonna copy the definition that we had above, but we're just gonna add more coefficient.
Okay.
So those guys will be a1 times x1 plus a2 times x2. This is not supposed to be a dot 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 dot. Up to an times xn, where all the AIs are inside of the ring.
Okay.
So basically what you do is you look at, so you start with some element x1 to xn, and what you look is at all the combination that you can make out of those, where your coefficient that you choose are inside of your ring are.
Okay.
Okay.
All right.
So this is a generalization of that, and you can check also this is an ideal.
So we got a question in chat. Hold on for a second. It looks like Ads is asking what book is Sascha following. Well, he's. Are you following a book, Sascha, or are you just basically restating this from like your own personal notes?
I mean, I'm not very following a book.
Yeah.
I'm just like restating like the
what your knowledge is.
Yeah, knowledge about ring theory.
That's how OG he is. He's basically just he made this just for us. Made this just for us.
Well, I mean, it's quite common to see in a ring theory course. So probably any good ring theory course will cover those things.
It's real analysis with ring theory.
Okay. And okay. Okay, I want to give you an example of an idea which is going to be important for us, because it's one of the examples that we can make of.
Yeah.
Is we're gonna take R to be the polynomial ring. So maybe I can take well, I guess I can work with rational coefficient. Doesn't really matter. Okay. Then what we can do is we can look at the ideal generated by some polynomial, and the polynomial that I'm gonna choose is this following polynomial: x squared plus 1.
Okay.
Okay. So I mean, this is just like a very concrete example of the notation that I used before. So I mean, if you want to make sense of it concretely, it's just all the multiple of this polynomial. So it's all the.
Is that supposed to be q1 or just q multiplied by
q multiplied by x squared plus 1, where q is just some polynomial.
Okay.
Okay, so this guy will be important. I mean, you will see.
So is the q with the square brackets around the x, is that supposed to be like the equivalence relation?
No, so this guy is just a parent. So the branches here is just for the arithmetic. So just I want to multiply this polynomial with this polynomial.
Oh no, I meant this one.
Oh, this one? No. This is just a notation to say that q is a polynomial.
Oh, okay.
So as I said before, this is the set of all polynomial.
Okay.
With q coefficient.
Okay.
I mean, you can do some variation of that. For example, if you put, for example, the r like the real numbers, then you will get all the polynomial with a real coefficient. Okay, there's like, I mean, the little symbol before just tell you what's the coefficient.
Yeah, I think Ads is a little bit wondering about like what we're covering, like since we're covering rings. Like they basically said rings are covered like the next day after introing groups, and we haven't done groups. This is just Sascha's way of basically trying to explain where the numbers come from. He's trying to reduce I guess what do you call it, the typical way that real analysis is taught.
Yeah. Okay. So I mean, as the core, ideals are subset, right?
Mm-hmm.
And we have an equivalence relationship on the set of ideal, which is inclusion.
Okay.
So maybe I will state as below. So ideal are partially ordered by inclusion. Okay.
Are partially ordered by inclusion. So what is that supposed to mean?
So it means that we have a way to say if ideals are bigger or not sometimes.
Okay.
For example, you would say that, for example, if we go back to the integers, that 4z is contained inside of 2z.
Okay.
Maybe I will leave you wonder why.
I'm guessing because 4 is an even number.
Yeah.
That's why.
So if you take a guy which is a multiple of 4, then of course it has to be a multiple of 2. So you get this. So you get those inclusion, right?
Uh-huh.
And so what you will say is you will say that 2z is a bigger ideal than 4z, right?
Yeah, that sounds about right. Yeah.
Yeah. And but I mean, as the name might suggest, it's a partial order. For example, you cannot make sense of is 2z bigger than 3z.
2z is bigger than 3z?
So this,
is that what you wrote?
Yeah. Okay. So this you cannot make sense of because the two sets are not. I mean, there is no inclusion relation between the two.
Oh.
So if you're a multiple of 2, it doesn't mean you're a multiple of 3, and the other way doesn't work. Okay. In fact, you can sort of see how the ordering will work on those ideal. So usually you will have something like that. So maybe I can give you an example. You will have the 0 ideal at the bottom, which everybody contains.
Okay.
And you can have like I don't know something like xz, like something like that.
Are we gonna have like the big circles again?
The big circle? What?
Like you remember you drew a circle?
Oh yeah. No. No. Okay, maybe I can choose something else than 6. I will take something which has a lot of factor maybe. So what about 12 maybe? Okay, let's take 12z. So those guys are the multiple of 12, okay?
Okay.
So the multiple of 12 will be contained inside of the multiple of 6.
Okay. Wait, what did you wrote underneath 6z?
So it's just the inclusion symbol with the. Well, I guess I don't have to put the equal sign because they're not.
Oh, those are like union, right?
Yeah.
Oh, okay.
But not union, inclusion.
Oh, okay.
So every element of all multiple of 12 are multiple of 6,
okay.
And I mean you have a lot of inclusion. After that, you can have this guy is also contained inside of the multiple of 4 because 12 is divisible by 4.
Kind of reminds me of those category theory charts.
Yeah. So I mean, basically, if you want to know which ideals are bigger than your ideal here, you just look at the factor of your number.
What question do you want to ask ads? Because ads wants to ask a question on the stream.
Okay.
Let's see. Unless you're asking someone else in chat a question, because it seems like ads and let's see, dissident. They're basically discussing about like probably the way we're learning this material. Oh, you're gonna ask later? Okay. Continue on, Sascha.
Okay. Okay, maybe it was a bit messy, but I just want to say that, and as they are a subset of a set, you can make sense of partial order like inclusion. Okay.
Okay.
Okay, but it will be, what we would like to define is to look at maximal ideal. Okay, so maybe I will introduce a definition, which we're gonna care for today.
Okay.
Is the following. We say that so we said that an ideal I inside of R is maximal if we have the following condition, okay?
Okay.
1, I is not equal to R. And secondly, I is maximum. I guess in English you're supposed to say maximal. It's maximal.
What does it mean to be maximal?
Well, okay, maybe I'm tripping a little bit with the language. Is that really not the way that people write it in English?
Usually I hear maximum.
Yeah, those two. Okay. Okay, it's maximal. Yeah, it's maximal. Yeah, that's an English word. Okay. So maybe I will not trip, but I think it's the same in French and English. Okay, so in French we also have similar words. So we have maximal and we have maximum.
Okay, because like you
which are
and you're just defining what an ideal in the ring is maximal, right?
Right. Yeah.
Okay, you're just giving the conditions. Okay, never mind.
Yeah, and maximal is also a word that you can make it makes sense in English. So what is the difference between maximal and maximum? So a max. So basically, okay, here it's a very okay. Maybe I should not put too much emphasis on this because it's not very that important. But
what is it that you wrote for number 2? The ideal is maximal.
Yeah, I was not done with it. I was
Okay.
I was just trying to explain what maximal is. But
yeah,
okay,
go
maybe
on.
I will write the definition. I will explain the nuance. I is maximal. Okay, maybe I will just restate the first condition. So the condition that I is not equal to R is called being proper. He is a proper ideal of R. That's another way of phrasing it, okay?
So, if it's a proper ideal of R, does that mean that everything contained in the ideal is not within R?
So it means that it means that the ideal is not equal to the whole ring. It's strictly smaller.
Oh, okay.
So there's like some element inside of
it's similar
R
to
which is not inside of I.
So it's similar to say like like A is a proper subset of B.
Yeah, exactly.
Okay.
So I is maximal among the proper ideal.
Okay.
And maybe here I will explain a little bit of the nuance. So as you said, you have kind of two words in English which looks the same. You have maximal and you have maximum.
Mm-hmm.
And the difference is very like, I mean, when we talk every day, we don't really do the difference between the two. I think even maximal is not very used too much when people are speaking.
Yeah.
But so what maximal mean?
Mm-hmm.
So okay, maybe I will give you the real definition so we can maybe leave the ambiguity.
Mm-hmm.
So let S with the partial order.
Okay.
I mean, it's not very important, but I just want to
Clarify.
clarify because it's kind of a cultural thing that which sometimes is important, but yeah, the distinction is kind of.
So it's
minor,
like S with a. Is that S with a subset symbol?
Yeah, but it's less or equal to. So it's just a partial. It's just a partial order relation, like we saw.
Okay.
A few weeks ago. So we said.
Let's see here.
so we said it. So if I have a partial order and maybe we're gonna call it with a big M.
So does this say let S and the less than or equals to sign be a partial order?
Yeah.
Okay.
So a partial order could be like, for example, less or equal for the inside of the integers, or it could be the inclusion. I mean, it's just a general partial order. It does have a. Okay.
So the definition, we say that an ideal is a subset of the ring, or I guess like within the ring, is maximal if we have that the ideal is not equal to the ring, right?
Yeah.
And then we're on the second one, where it's like the is maximal among the proper ideal.
Yeah, I should probably clarify the of R.
Of R, okay.
Okay. And maybe let me just give you the definition. So maximal is called maximal if for all n inside of S.
Yes.
Okay.
Okay.
Which are comparable with M. Which are comparable.
Is M just a number in this case?
No, M is just an element of an abstract set, which have a partial order. So it could be a number, or it could be a subset. I mean, it can be it's just an abstract notion.
Okay.
Which are which is, maybe I should say, which is comparable with M. Okay, so we're able to say if N is less than M or M is bigger than N. So for all such N, we have that N is less or equal to M.
Okay, so you said M is like a subset of S?
It's an element of S.
Oh, it's an element of S? Okay.
Yeah. And so this is the definition. So this is the definition for maximal. And likewise, we said that M is maximum. So M is maximum if well, we have two conditions. First, for all N inside of S, N is comparable to M. Comparable with M. And secondly, M is maximal.
And this is you just comparing the wording maximum and maximal, right? Because you said M is maximum if okay.
So maybe I will give you like the idea of between the distinction between the two. So for example, in the case of inclusion, sometimes we cannot compare two subsets, right? So this condition that N is bigger than M does not always make sense, right?
Okay.
It just makes sense when N can be compared to M, right?
Right.
So that's the that's for maximal, and in maximum the condition is stronger.
Okay.
Because not only you want to be the biggest among all the one that you can compare, but you also ask that every element inside of S is comparable with M.
So basically, like, in order for it to be a maximum, it has to be a maximum, but it's not the other way around.
Yeah, so this guy, maybe we should think this guy is the maximum.
Hence the wording.
Yeah, and this guy is a maximal. So as you may be able to read, in the first case I used the word A, right?
Yeah.
So a maximal element is not necessarily unique.
Okay.
You can have multiple maximal elements, and in the case of the maximum, then you only have one.
Is it like, I guess, like similar to like when we are in calculus, like you have like extremum, like categories of extremums, where it's like you have like the absolute maximum, but you have like a maximum that's like not as low,
well,
not as high as like a previous one. Like, you know, like say if you have a curve that has like two what is it, like two maximum points.
Yeah, so it's not exactly the same because, okay, for example, if we take like the less or equal symbol inside of the real number or the rational, it doesn't really matter. The thing is, this symbol, every element is comparable, right?
Which symbol?
The less or equal symbol inside of Q is every element is comparable, right?
Yeah.
Like, okay, in Q, given the less or equal symbol, the usual one, the two notions are equivalent. Well, okay, here the condition is a little bit vacuous, but
Yeah. Is that a B or Q?
It's supposed to be Q.
Oh,
yeah,
Q.
but okay,
Q.
yeah. Maybe I should change a little bit because this is not very good example because inside of this set there is no maximum nor maximal element. Because Q is not bounded. There's like always a bigger rational number. So
okay.
There is no thing. But for example, if we take, I don't know, maybe the closed interval 0, 1.
Okay.
Then this guy will have a maximum and
a maximal.
Yeah, but the two will be the same.
Okay.
Basically, the reason is because every element inside of this set are comparable. You can always make sense of is 1/2 bigger or less than, for example, 1/4. So everything is comparable. So the first condition in maximum is automatically checked. Yeah, I guess it's getting a bit messy. I'm sorry.
No, it's okay. It's just the bot ads. I just put that in there because before, when I was streaming, I would do like problems, and sometimes like I know a lot of people like are very passionate and basically telling me the answer when I'm like struggling with problems. That's the reason why it just does that.
Yeah. Okay. So I will give you example of maximal ideal. Okay. So we're gonna look at Z. Okay. Let P be a prime number. Oops. Then PZ is a maximal ideal. Okay. So maybe we can check this is a maximal, so we need to check a few things. First, we need to check it's not equal to the whole set, right?
All right.
So first question is PZ equal to Z. So that's the first question. So what do you think?
PZ equal to Z. Okay, so P is a prime number, then isn't I? Ooh, that's an interesting question, actually. I'm having like multiple like prime numbers in my head.
Yeah.
and I'm like trying to like combine them with integers, and I'm like, wait. Is that true?
maybe we can take a more simple example. Okay, maybe let's specialize the case where P is equal to 2. So the question is 2Z equal to Z?
Okay. I would have to say.
So what is the guy on the left?
The guy on the left is basically just the integers multiplied by 2.
Yeah. So those are the multiple of 2, right?
Mm-hmm.
But if you're like talking to a 12-year-old, what were you saying? Like,
I mean, they don't seem to be equivalent because then
no. Yeah.
because like typically like all it's just the even numbers if it's just multiplied by 2 with them.
Exactly. So those are just the multiple of 2, as you said. They're just the even numbers. So you can,
Mm-hmm.
for example, 1 is not inside of this, right?
Mm-hmm.
So this give you I mean, so you see that those are not equal. You have a strict inequality, and the same reason goes for p in general when p is prime.
Right.
Because if p is prime, 1 will not be inside of this guy.
Yeah, that's why I was thinking like that probably can't be right because it's like
Yeah,
every prime number is like that's why like I was like that was kind of funny if it was like the same, if they were equivalent to each other.
Yeah. So those are not equivalent. Those are just those are not equal. I mean, they're just, you have a proper subset. So we've checked that PZ is a proper subset. Okay. Now we have to check that PZ is maximal. Okay.
Okay, so PZ is maximal, right?
Yeah. And what you do usually is that you suppose it's not the case. Okay.
Okay.
Suppose otherwise. So maybe here I will use a little bit of arithmetic that you may not know, but I mean, we can take those for granted because I mean, at the end it's just the ring theory that I cannot arithmetic too much. So suppose otherwise. So there exists an ideal M, which is, okay, maybe I should write like that, which is not equal to PZ, which is also proper inside of Z. Okay.
Okay.
In particular, there exists an element inside of M, which is not inside of PZ. There is some X inside of M, such that X is not inside of PZ. Okay.
Okay.
Is that so good so far?
Okay, so basically, suppose otherwise, like PZ is, I'm guessing that is supposed to represent proper subset of M, right?
Yeah.
And proper subset of Z. Okay. In particular, there exists an X in M, where X is not an element of PZ. Okay.
Yeah. And I forget something very important. Here, I want M to be an ideal.
Okay.
Okay. And now we're gonna use a little bit of arithmetic. So we're gonna use the fact that so as X is not inside of PZ, right? That means that X is not divisible by P.
Okay.
Okay. Therefore, they're co-prime. I don't know how you. I mean, are you familiar with the greatest common divisor?
Yes, I've read about that. Yeah.
Okay. So one way to say that is the greatest common divisor of P and X is 1.
Right, because it's supposed to be a prime number.
Yeah.
Like...
So the only divisor of P will be P in itself. So if P does not divide X, then it has to only be 1. Okay. And now we're gonna use a little fact about arithmetic. We're gonna use Bézout identity. Are you familiar with that?
I feel like I've seen the word before, but I'm not familiar about what it is.
So what it tells you, so I will state it in general. If A and B are inside of Z, you might want to assume that A and B are not 0, otherwise you can run into some weird problem.
Okay.
Then there exists X and Y, integers numbers, such that they satisfy the following equation. So maybe I can give you an example of the Bézout theorem. So for example, if we choose A is equal to 2 and B is equal to 3, okay? What is the GCD of those two guys?
For A and B, the greatest common divisor.
Yeah, if A is equal to 2 and B is equal to 3.
Practically be 1 because they're both
Yes.
prime numbers.
Yeah, they just share 1 as a common factor.
Hmm.
And so here we can find the x and y very easily. So they will just be given by 3 times 1 plus 2 times minus 1.
Okay.
And so for this example, it was very simple. So we were able to just kind of play with the number and find the x and y that works. But usually it's a little bit more involving. You need to use the Euclidean division and facts about GCD to be able to find those coefficients, but I will not spend too much time on that. But if we were doing a little bit more arithmetics, we would be able to prove a Bézout identity like that. Okay, and now what we're gonna do is okay. So this was a digression to explain what Bézout identity is.
Okay.
Now we're gonna apply it to the case that we care.
Okay.
So let's go back to the situation we were. So we had P, which is a prime number, and we know that the X is a number which is not divisible by P. Therefore, by Bézout, they're gonna exist X and Y inside of the integers such that Px plus so what was the other guy? It was called, oh shoot, I called two things X. I shouldn't do that. Let me call it Y and Z then. So we have Py times Xz, which is equal to 1. Okay.
Okay.
But then now we get a contradiction. Okay.
Okay.
Why is that? So
let's see. Therefore exists z part of the element of this integers p times y plus x times z equals 1.
So explain why we get a contradiction here. So the problem is that P is inside of PZ, right? I mean, obviously.
Yeah.
This guy is a multiple of itself, of course. Yeah. And we have that M is maybe I will write it like that. We have those inclusion, right? And the X is inside of this guy, right? So what happened is that P and X are both inside of M. So therefore, because of the axiom for an ideal, if I have a linear combination of elements inside of M, this guy must also be inside of M. Do you see why?
Let me take another look. Let's see. P is PC, which is a subset of M, which is a proper subset of M. I think the contradiction is basically since it's an element of M, right? Because I'm looking at that it should be a proper subset of M, right? Which means that none of the elements within PZ should be an M.
No. No, the fact that it's proper just means that there's elements inside of M which are not inside of PZ, not the other way around.
Oh, okay.
Otherwise, it will not be a subset.
Okay.
So okay, maybe here I'm kind of asking you a little bit too much because you kind of have to see it once. So do you agree that Py and Xz are inside of M?
Yeah.
Because M is an ideal.
Mm-hmm.
So, so as P is inside of M, if I multiply it by some element of my ring, for example Y, this should still be inside of the ring, right? Inside of M, right?
Uh-huh.
And the same goes for when I multiply X by Z, right?
Uh-huh.
But then I also know that the ideal are supposed to be closed on the addition, so this whole sum must be inside of M.
Uh-huh.
Because M is an ideal. But what was this sum equal to? It was equal to 1, right?
Yeah.
Does 1 is inside of M. But now we're kind of screwed. Because if 1 is inside of M, now we are very screwed. Because then for all N inside of Z, we can write N times 1, right?
Oh, okay.
Do you see the problem now?
Yeah, because like let's see.
It has to absorb, right?
Because like N is supposed to be part of Z, and so I feel like I'm kind of seeing a connection, but at the same time I just can't phrase it.
Okay, so maybe I will give you a help. So so one of the axiom of an ideal is that when you multiply it by anything, when you have an element of your ideal and you multiply it by anything, it should still be inside of the ideal, right? So the fact that we have 1 inside of our ideal will force that when I multiply 1 by N, this has also to be part of M, right?
Okay.
Thus, we have that N is inside of M. But this is a contradiction because we've just shown that every element of Z is also inside of M.
Okay.
Therefore, Z is equal to M.
Oh, okay. And it's supposed
which
to be
contradicts right? Yeah.
Because M is supposed to be a proper subset to Z.
Yeah. Okay, we're gonna look at another example of a maximal ideal. So for this time, I will take R to be the ring of a polynomial with rational coefficient, and we're gonna take our ideal to be the ideal generated by the multiple of x squared plus 1. Okay. And this guy is maximal. Okay. And the proof is going to be very similar, okay? So we're going to assume it's not the case. Okay. Then we're gonna basically have the same setup. We're gonna have x squared plus 1, which is stuck between a maximal ideal and the entire ring, right?
Okay.
Where M is, well, I guess I will just say M is an ideal. I don't need the fact that it's maximal. In fact, we sort of have to show that every ring has a maximal ideal, but I will skip over that. Okay. And now we're gonna basically try to have the same problem, okay? So as the inclusion of this idea is not so as the ideal generated by x squared plus 1 is proper inside of M, there means that there exists some M which is not inside of x squared plus 1, right? Just as the way we did before. There exists some Q inside of M, such that Q is not inside of the ideal generated by x squared plus 1. Okay? And now basically we're gonna see the same pattern. So Here's there's something funky about x squared plus 1. Do you know what it is?
Let's see. So there exists a q that's in M, and q is an element of x squared plus 1. And let's see, the real... Oh no, the ring is equal to the... is proper set, where M is an ideal.
Oh shit, this here I'm supposed to write not in contain, I'm sorry.
So rephrase your question again.
So okay, maybe my question is not very clear, but what we're gonna show is that basically x squared plus 1 sort of behave like a prime number. Okay. And what I mean by that is that x squared plus 1 does not have any non-trivial divisor. Has no non-trivial divisor. Do you see why?
Non-trivial divisor.
So maybe here I can clarify. So you can always divide a polynomial by a constant, right? But those are kind of like not very useful, so those are usually called trivial divisor. It's kind of like it's pretty much like the way that, for example, in Z you can always divide by -1 or 1, but I mean those are trivial divisor. They don't really do much, right? So here what we're gonna show is that x squared plus 1 has no divisor except itself and the non-zero constant. I.e. the only divisor are itself and the non-zero constant. Okay. And do you know how we do that?
Okay, so non-zero constant divisor itself and zero constant. I'm trying to remember the divisor proofs in my head, but that's probably not the right approach.
So maybe I will guide you because it's kind of the first time you see that, so I don't expect you to do that. So except otherwise, okay? So first of all, because of the degree, if x plus 1 has some divisor which are non-trivial, they have to be of degree 1. Otherwise, you're gonna blow up the degree.
Okay.
If it has divisor, I mean non-trivial divisor, they have to be of degree 1. Okay? Therefore, what you get is you get that x squared plus 1 is equal to x minus a, x plus a, let's say, times x plus b. Well, I guess we can put a minus, doesn't really matter. Where a and b are rational.
So like the first sentence you wrote, if it has a non-trivial divisor, I'm guessing then it has to be what is the part between 1 and b in this? It has to be, what is that?
Degree 1. They have to be degree 1. So
okay.
Non-trivial divisor, they have to be degree 1.
Okay.
So that would mean that x squared plus 1 can be factorized as follows, right? But this is a contradiction because a or b are supposed to be rational number because we want those polynomials to be rational, right? It only makes sense if the coefficients are rational. But then that would imply that x squared plus 1 has a rational solution, which cannot happen. And the reason why it cannot happen is because, for example, the square of a rational number is always something positive, and if this equation has a solution, then the solution would have to have they will not follow this principle, which cannot happen. Okay. So this guy is sort of the I mean, those polynomials are called irreducible, so they mean they cannot be factored out as a polynomial of a lesser degree. Okay. And those are, I mean, at least from the ring theory point of view, those are really like the prime numbers inside of the integers. They behave quite similarly. And okay, so what I want from this, so we can so there is so you probably found out from high school you have division for polynomial, right?
Yeah.
And you can also make sense of GCD for polynomial. And the Bézieux theorem. So the Bézieux theorem works in this setting. So maybe as Q is not inside of the multiple of x squared plus 1, right? Then that means that x squared plus 1 does not divide Q.
Okay.
Thus, that's what we get. Thus, we get that the GCD between those two polynomials has to be 1. So they are coprime. Because x squared plus 1 has no non-trivial divisor. The only divisors are constants. And now what Bézieux is going to tell you is Bézieux is going to tell you in the case of the polynomial, it's going to tell you that there exist P1 and P2, two polynomial with rational coefficient, such that P1 times x squared plus 1 plus P2 times Q is equal to 1. So this is Bézieux for polynomial. Okay. So maybe I can give a word. So basically, in every ring that you have like the Euclidean division that works, for example, in the integer or the polynomials, you will always have a version of Bézieux theorem that's gonna hold.
Okay.
And even stronger, you're gonna have a stronger of the fundamental theorem of arithmetic that's gonna hold also for this ring. So every polynomial can be written as a unique factorization of irreducible polynomial. So that's why I'm saying that x squared plus 1 is pretty much like a prime number for the polynomial over the rational.
Okay.
So we get that, and for exactly the same reason as I mentioned in the case of the integers.
Yeah.
So we have x squared plus 1 is supposed to be an ideal content inside of M, right? Therefore, we must have that x squared plus 1 is inside of M, thus we have this whole sum has to be inside of P2 times Q has to be inside of M. So maybe I should recall that Q was initially inside of M also. Okay. But then we get exactly the same problem as the integers. We get that 1 is not inside of M, and for exactly the same reason as for the integer, this implies that M has to be equal to the whole ring. Because once you have 1 inside of your ideal, you're really screwed, because you can just multiply by any other element of your ring, and you will still get something which is inside of M. So we're screwed. Thus, this ideal is the is maximal. Okay. I hope I give you a little some example of maximal idea and a little bit of an idea how to show their maximal.
I'm pretty sure I'm gonna have to go back in my notes
Yeah.
and basically solidify this idea.
Yeah.
Because some
yeah,
parts
I kinda
some parts I felt like I followed, and some parts I was like, wait, what?
yeah. It's basically because I use probability of polynomial, which are maybe not very. Maybe you don't really know, like Bézout theorem, stuff like that. Okay. Okay, now I'm gonna introduce a notion which is gonna be important for us, is the idea of a quotient ring. So again, we're gonna let R be a commutative ring. And I is an ideal, okay?
Okay.
Then we can have an equivalence relation on R. And I will pretty much leave the check that it's an equivalence relation as an exercise and some of the property, because I kind of want to give you one very cool example before we go today. Otherwise, I will just state some very abstract theory. Is an equivalence relation. So we have the following equivalence relation. So we say that x and y inside of R are equivalent. Oops, sorry. X and y are equivalent if and only if x minus y is inside of the ideal I. Okay.
Okay.
And one of the exercises is to check that this is indeed an equivalence relation. Okay.
Okay.
Okay. And okay, this I will skip. So usually the quotient that you get, so when you mod out by the equivalence relation, you get the quotient ring, which we usually denote by that. So this guy is R modulo the equivalence relation that we introduced above, okay? So the way you usually want to think about the quotient is that now the element inside of your ideal I are now zero inside of the quotient. Okay. And okay, maybe here I will basically tell you. So you have to do a verification, but it's kind of a lengthy one, and I want to give you maybe one example.
Okay.
So I will sort of just tell you what's the end result, and I will put in the sheet some guidance to show that. Okay, I will not leave you alone with showing that. I will give you some kind of exercise with multiple parts where you can. I mean, if it's too hard, I can do it for. We can talk about it later, but the point is that R over I has the structure of a ring.
Okay.
And the way it works, so this guy is a quotient, right? So this guy is made of equivalence class of number inside of R, right? And the way that addition and multiplication will be defined are basically the obvious one. So those guys are inside of the quotient. So I put square parentheses to say that you're equivalence class, right? And then the addition will just be I will add them like that. And I will do the same thing for multiplication, okay?
Multiplication, okay.
Yeah, but this is not obvious that this is well defined, because maybe this definition depends on the specific choice of x and y, so we have to make sure that's not the case.
Okay.
Basically the way that we did for the integer, the rational number, we already had to do those kind of check. Then we also have to do those kind of check on the quotient, okay? But there's not really much that's happening. It's just like you have to make sure you understand the definition, and just you unravel the whole thing, and then you just get that. It's not that hard. You just have to make sure that you understand the definition.
Mm-hmm.
Okay. And now I'm gonna use a proposition that I guess I will also put on the sheet. I might write like some note where I give the whole proof on a PDF, because it's kind of a lengthy thing and I don't want to spend too much time on that.
Mm-hmm.
Well, at least I would like to give you like more example on the stream so you can have a better idea, rather than spending like half an hour doing like some proof.
Yeah.
Which is not very helpful. So the proposition is if I is a maximal ideal, then the quotient ring, R quotient by I, is a field. That's a very strong statement. The proof is not too hard, but as I said, we'll probably write some notes for if you're interested. But I will give you example of application of that. Okay.
Okay.
And I will show you how to do the computation, and you will realize that we create a very special number that is very famous. Okay.
Okay.
So you're gonna see. I mean, it's kind of magical the first time you see it. When I was an undergrad, that was definitely one of the magical parts of the first ring theory class.
Oh.
So let's take our ring to be the rational number.
Uh-huh.
Well, actually, it's gonna be even funnier if you take the real numbers. Okay.
Okay.
I mean, here I'm gonna cheat because we haven't defined the real number, but let's assume that we did. I mean, this fact is independent of the fact that we create the real number. I mean, we're just gonna assume it because it's even, I think it's even cooler. And okay, here I haven't showed it for the real number. I've showed it for the rational number, but basically the exact same proof show that this ideal is maximum. Okay.
Okay.
Basically, the reason is the same as I stated before: is that x squared plus 1 cannot have a factor of degree 1, because otherwise they would have to be root to the equation x squared plus 1 is equal to 0, right? Which cannot happen over the real number. So this guy is maximal, okay? Okay, and are you ready to get your mind blown?
I guess, yeah.
Okay. So we're gonna consider the quotient ring. Okay. And now it's a thing that you know for sure. Okay.
Okay.
What it is. It's so as the proposition said before, it's supposed to be a field. Because I is maximal, so our quotient I is supposed to be a field.
Okay.
Okay, are you ready?
Yeah.
So we're gonna do some computation, okay, inside of that. Okay, first of all, I will probably state the division algorithm for polynomial here. Just to make sure that we're on the same way. I'm pretty sure you already did like the long division for polynomial, but I will just restate it, okay? So, so the division algorithm say the following. Well, I guess I will specialize for this guys, okay?
Okay.
It said that if you give me any polynomial inside of R, then P can be written as Q times x squared plus 1, which is the thing I want to divide, plus some remainder, right? And degree of R is less than the degree of x squared plus 1. Maybe we can do like one example. And also the theorem said that Q and R are unique. Also, Q and R are unique. Okay.
Oh, so it's like degree R, right? And degree.
Yeah.
Okay.
So it would be a degree less than 2, so it would be degree 1 or constant. So let's maybe take P to be like some polynomial. Let's take something easy. Let's take x cubed, okay?
Okay.
And now let's do the long division. So I want to compute. I don't know how you write your long division, but I personally write something like that.
Okay.
Okay. And now we're gonna do long division. So what number I have to multiply x squared to kill this x3? I have to multiply it by x, right?
Yeah.
So I'm gonna get x cubed minus x, plus x, sorry. So x cubed, we're gonna kill them off. So we're just gonna get a minus x, right?
I think you're like, you're not, when you were writing something, I think it cut off when you were writing like x cube, like, and like it stopped right there.
Okay, do you see now?
Like I can only see like the x cube here.
Okay,
but I don't know if you wrote anything afterwards.
Yeah, I wrote something, so maybe I will just rewrite. So do you see it now?
I only see like a line.
Okay, I guess I will.
Yeah.
I guess I will refresh my page. Oh gosh.
Yeah, this usually happens when we're doing this.
Well, it has to happen once the stream, right?
Yeah, once a stream, yeah.
Oh god. Can I? Okay. Do you see my? Oh, maybe I will.
I see your cursor.
Do you see my the thing I just draw?
I saw a squiggle line that you made.
Okay. Am I on some text or am I like below it?
You're just basically over the squiggle that you drew.
Okay. But is this okay? If I write like here, is that fine? Or am I like over some other text? Because I don't see the thing that's written right now.
You just made two squiggles.
Yeah, I just made two squiggles. Are those squiggles like below the existing
Yeah,
text?
they're below the text. They're below the text.
Okay. So, okay, we're gonna do the example again. So, let's do x squared divided by x squared plus 1, okay?
Okay.
So we're gonna just divide by x cubed plus x. So we're gonna left with a remainder of minus x, right? Therefore, we can write x cubed as x time x plus 1 with some remainder, right? And here the remainder will be minus x, right? Okay. And this guy, I mean, the division algorithm is kind of like the king to compute what is going on in the quotient.
Okay.
Okay. So maybe I will just rewrite on the so our quotient is the rational number. I mean, I said the real number because it was even cooler. Okay. Are you okay? And okay. I don't have the division algorithm in my face. I will just rewrite it. So the division algorithm says something like that. Just some reminder, right? And I mean P and Q and R are unique. Okay. And okay. So what was the equivalence relation of that guy, right? So we said that two polynomials P1 and P2 are equivalent if and only if their difference is inside of our ideal, right? That was the equivalence relation that we had. Okay. So if we look at the example we had here, what we can do is we can do some rewriting. Okay. First of all, we can take the x, so we can take the minus x on the other side and moving to the other side. Okay. Okay. Do you see, Peter? This is this. I use this equality.
Yeah.
Okay. And now if we use our definition, so this guy is a multiple of x squared plus 1, right? I mean, it's literally like a polynomial times x squared plus 1. So this guy is inside of I. Therefore, in the quotient, x cubed and minus x are equivalent. Okay.
Okay.
And more generally, if we use the Euclidean division, what we have is we have that P and R. P and O. I wanted to write P and R, and I wrote the verb. P and R are equivalent. Oh, that's a weird thing to say. Are equal if we want, or equivalent. In the quotient. Okay.
Okay.
And the fact that Q and R are unique means that basically, if we want to look at two polynomial and if we want to know if they're equal in the quotient, we just need to check if they have the same remainder.
Okay.
Okay, that's a pretty neat thing. Okay. Therefore, as I said, the remainder is degree less or equal to x squared plus 1. Right?
Okay.
R is always of degree less or equal to 2. So R will always be some kind of polynomial that looks like that.
Okay.
Okay. So in the quotient, every element looks like that. Okay.
Okay.
Where A, B are real numbers.
Okay.
Okay. And now are you ready? Okay.
Okay. I don't believe you, but okay.
Okay. Are you ready?
Yeah.
Okay. So now I will teach you how to do multiplication inside of the quotient. Okay. And then we're gonna have a fantastic fact. Okay.
Okay.
So let's take two elements inside of the quotient. Let's take R1 and R2 inside of the quotient. So R1 will be given by A1 plus B1x, and R2 will be given by A2 plus B2x, okay? Now we're gonna multiply those two together, okay?
Okay.
And we're gonna see what's the answer inside of the quotient, okay?
Okay.
So what we're gonna do is we're gonna just do the usual polynomial multiplication, and then we're gonna look at the long division result when we divide by x squared plus 1. So let's just do the usual multiplication as usual. A1 plus B1 times x times A2 plus B2 times x. Okay, so what does this thing give you? It gives you something like A1, A2. What do we have next?
I think the next one
we have
is... Yeah.
Oh yeah, then I get some cross term. Okay, plus B1, A2, those guys times x, plus B1, B2,
and then
x squared.
Yeah.
Yeah. But now now we just did the multiplication in the usual polynomial, but we want to know what it does, what it looks like in the quotient. Or maybe it was not such a good idea to do it like that, but I guess we're gonna bear with it.
Yeah.
But it's okay. B1 B2 x squared plus. Maybe I should have just shown you the mind-blowing fact first, and then show you the multiplication.
Fine.
But it's kind of.
We're already this far in anyway, so might as well go for the long haul.
Yeah, I guess we're gonna see the entire multiplication.
Yeah.
Okay. Okay. So what do we get here? we get a mess. Okay, B1 times B2. Oh yeah, I don't think I want to do the entire. Okay, I will just. Okay, I will do it. Okay, we are brave enough. Bear with me, me, Peter.
Yeah. Storm. Pain basically says to make it easier when you are in the quotient, you need to think of x squared plus 1 as a zero polynomial.
So okay, let's write what the result is. So the result will be a1 b2. Oh, it's not that bad actually. Okay, maybe I will write the other way. So it's gonna be a1 a2 minus b1 b2 plus what are we left with? Oh, we're left with that guy. So we're left with a1 b2 plus b1 a2 times x. Okay. Okay, now it probably doesn't ring you a bell, okay? But I would maybe I should have done like the general case, but okay, let me do the special case with matter. What happens if we multiply x with itself? So we get x squared, right? But now let's look at the division when we do x squared plus 1.
Okay.
So here we get a 1, right? So we get with x squared minus x squared plus 1, so we're left with a minus 1. Does x squared in the quotient is equal to minus 1?
Okay.
Does it ring a bell now?
Yeah, the complex numbers.
Yeah. So the x is actually, I mean, okay. Actually, the ring that we just create, which is our x time quotient out by x squared plus 1, is nothing else than the complex number.
Okay.
And so I mean, basically every element inside of this quotient can be written as a plus bx, right?
What did you write in between the complex numbers? What is that?
Maybe I should put just an equal sign. Was
is a less than or equal sign?
Well, it was an equivalence sign, but
it's an equivalent sign. Okay.
Yeah, and that's usually, I mean, that's one way of defining the complex number, is to look at polynomial over the real number and quotient out by x squared plus 1.
Okay.
And you get that. And then the quotient, you get a plus bx, which is, I mean, if you translate to what you usually know, it will be a plus bi. And basically the computation that we did before, the long one, which I should have done, this guy, basically, if you were a bit attentive about complex multiplication, you will find that this is the usual complex multiplication that you usually get.
Oh.
When you multiply a1 plus ib1 with a2 plus ib2.
Yeah,
when you do this multiplication, you're left with that.
Yeah, Storm Dupin basically said here he makes a lot of computation for nothing.
Maybe I should have shown it.
Let's define like pi to pi being the, I think, like the real number relation of x, because like they type something up and then like I think like our relation to big X over the ideal, the projection, then you need to know that pi times p plus q is equal to pi times p plus pi times q.
Yeah.
So it's like
this we mentioned.
I think it's restating the definition.
Yeah, I mean, I kind of skip over this check that's showing that when you have an idea and you quotient by it, you actually get a ring.
Which part?
But I mentioned, I mean, at the very top, when I guess I cannot see it anymore, but when I was talking about if you have an idea and you and you have this equivalence relation on your ring, then the quotient set that you get is actually a ring. And the way I stated was that the addition and multiplication will carry out on the quotient set, which is exactly the same way that Storm is writing that the projection from the ring to its quotient ring will be a ring morphism, which means that preserve addition and multiplication. Usually those kind of, I mean, here I kind of check like for a general element, but what you will usually do for understanding the multiplication on the quotient ring would be to take a basis.
Okay.
Because basically this guy, I mean, we're gonna do it maybe in linear algebra, but when you quotient by this guy, 1 and x would become a vector space basis, and basically you just need to know what multiplication does to this basis to understand the full picture. But we haven't done that, so I kind of did like the ugly way, but
it's fine. An interesting example, if you want, let's see, r is in x, the division of x squared.
Yeah, okay, yeah, you can do some funky quotient like that. Okay, maybe I can give you another one, which is kind of cool.
Okay.
Okay, maybe I can just give you some insight, okay, about what we usually think about it. Okay.
Okay.
So usually we don't. I mean, this is like a very like formal way of thinking about it. Usually, what we think about it is that the idea is giving us some relation. Okay.
Okay.
So what is basically telling you is that so the quotient will be essentially the polynomial, but you also have the equation x squared plus 1, which holds. Okay.
Okay.
So this is kind of a new equation that you get. It's a relation that you get on the polynomial, and I mean that's usually the way you want to think about it. So just if you think about this way, right away you already get that x squared. So this implies in particular that x squared is equal to -1, which is the thing that we derive here. So maybe I can just give you another example. So if we take the polynomial with rational coefficient and we quotient out by x squared minus 2. Okay. You will get the rational number, but you added the square root of 2.
Okay.
So basically, every element will be written as I mean, at least if you want to think about it, will be written as a combination of a and b, where a and b are rational numbers.
Okay.
And you can basically do the same thing because when you will look at the quotient, okay, this guy is maximal. We can show it because it does not have a root over q. So what you're gonna get in the quotient is that every element could be written as a plus bx.
Okay.
Because here the degree is 2. Thus the remainder must be of degree lower, right? So it has to be degree 1. And the fact that x squared minus, so the fact that you quotient out by x squared minus 2 means that you have the relation, you have the equation x squared minus 2 is equal to 0 not hold in the quotient. So you basically get that x squared is equal to 2, which is pretty much the definition of a square root of 2. Also, a little fun fact that you can also tell is in the quotient we cannot really distinguish between x and minus x, right?
Right.
I mean, we sort of use x because we're kind of more used to it, but there's no really difference between picking x and minus x. I mean, at the end, they sort of have the same properties, right? Minus x squared will still have the property is equal to -1. And when we're talking about complex numbers, sometimes I mean it's more done like in some very formal French math book on mathematics, especially Bourbaki. they will usually say that if you choose either x or minus x, I mean, basically you cannot. There is not like a better choice between x and minus x. I mean, as the ring operation goes, there is no difference. They both like behave the same way.
Yeah.
And what they will usually say is that if you choose, for example, x to be equal to your I, which you think as your root of -1, then you made a choice of an imaginary unit. But there is also other choice that you can make.
Okay.
And like, I mean, if you look at when you look at Bourbaki, they will say, oh, we will consider the complex number, but we will not choose which one is I. Which is something a bit weird if you're not used to it, but
yeah, it feels like it's just like a roundabout way of actually like describing them.
The what?
It sounds like it's kind of like you're going in circles, just like to describe like complex numbers, like the way like you've written it. It's sort of like you're going like back and forth with certain definitions.
What do you mean?
No, I mean the way you were describing it. I mean.
Oh yeah. I mean, basically they will say we will not choose imaginary units, therefore the theory will be invariant under conjugation. But I mean, it's a very small detail that nobody really cares usually.
Oh, okay. That's fair enough.
Yeah, but it's just like a thing, and
okay.
Basically that's the way that we usually build fields.
So you basically build it from like a relation, but then you take the divisor of a particular like, how should we say this, like a particular set or ideal.
Yeah, so maybe I can give you like the way I like to think about them. So basically we have an equation over R, a polynomial equation x squared plus 1 that we cannot solve, right? We cannot solve the equation x squared plus 1 is divisible by 0. So what we're gonna do is we're gonna create a new ring where this relation holds.
Okay.
And basically, so basically what we just did is we just create like a new field where the initial polynomial that we were not able to solve now has solution. And that's pretty much like, the point of the complex number, right?
Right.
They were introduced because people wanted to solve polynomial equation over the real number, but some of them were not solvable over R, right?
Yeah.
So they sort of made up a new number called I, which has the property which solve the equation x squared plus 1.
Okay.
But if you want to do it a little bit more formally, that's exactly what we did here. We basically create a new set of number where the initial equation that we were not able to solve now has a solution. And that's pretty much the same idea for the second example. For example, square root of 2 is not inside of the rational number.
Okay.
So when we look at the quotient, we sort of introduce a new number called x, which is a square root of 2, which verifies the equation of x squared is equal to 2.
So, like, the reason why you're, like, showing this to me is, like, this, like, it's kind of like introducing how rings can allow us to create fields.
Yeah.
So, like, because from what I saw from your example, it's like we take, basically we take, like, like an equivalence relation within one particular set, but then divide it into, like, say, either a ring or an ideal. Or an ideal, I guess, from like the example you showed.
Yeah.
And thus that's
so the ideal gives you the equivalence relation.
And thus that's what gives you a field. Oh, okay.
Yeah, but the ideal has to be maximum, otherwise you don't get a field. You can get something else. Storm mentioned an example of sometimes this is called a dual number. Is you take Rx and you divide and you quotient out by the ideal generated by x squared. X squared is not maximum because it's contained inside of the multiple of x. That's not maximum.
Okay.
And in this, and basically if you look at what you quotient out by x squared, right? So in the back of your mind, you have to think of what will be the multiplication structure on that guy. It will be basically the polynomial, but now you have that when you have x squared, you now get 0.
Okay.
And so every number will be written as a plus bx, but now you have this funky thing that x squared is now equal to 0.
Okay.
And those are called the dual number.
Dual numbers?
Yeah. And one very cool thing that you can do is that I mean that's kind of a thing that which is interesting. If you have a polynomial and then you evaluate to I think it's something like that. Oh, here is going to be a bit of a mess. Let's see, is that something like that? Maybe I don't remember exactly. Okay, maybe we can look at a very concrete example. Let's look at let's look at this. So if you use the usual formula, you get a squared plus a times bx, 2 times a bx, I'm sorry. No, I think I just want x. I'm sorry. Oh yeah, I don't want the b.
Oh, you don't want the b. Oh, okay.
Yeah, so I think it would be something like that. Yeah. Oh, 2abx. Okay. Yeah. Okay. You will get something like that, right?
Do you want to erase the b in the what you put in the square?
Well, no, it's fine. I just want in the square. I just wanted to stretch the fact that every element inside of that will be written as a plus bx.
Okay.
But now we have the relation that x squared is equal to 0, so the last guy is vanished, right?
Yeah.
And now you kind of have a two-part, just like the complex number. You have if you want a real part and I mean it's not really the imaginary part, but another part, right? And so this guy, what it is just your function. Is just so you can sort of think as your initial polynomial as maybe I should write as something like that. Is equal to x squared, okay. Well, I guess that's not really a good notation, but okay. Maybe we can think about it like that. Let me use y because x is already used. You know what? I'm gonna use x anywhere. Okay. Maybe that's not a so great example, but so you have this function, right?
Is that supposed to be f of x is equal to x squared?
Yeah, I mean, usually you want to treat it as a polynomial, but let's not make the difference between the two. And what we did here is we just evaluate f of a plus x, right? And what it gives you, so on the left side, what you see is you just get the function of the value of f of a, right? And the other side, which contains the x, well, what is this quantity? It's kind of weird, right? You have a squared, and on the other guy you get 2a. Does it remind you of something?
So we get a squared plus like 2ax.
Yeah, don't worry too much about the x. You just care about the coefficient, the 2a.
So you're asking me if it reminds me of something, right?
Yeah.
Let's see. I mean, let's see.
Maybe I can do the more general.
Like,
because
like if it wasn't for the a, for some reason I keep thinking of the odd numbers.
Okay, maybe we're gonna do a more general case, because I guess on one example we cannot really see it. So let's have a look at this, okay?
Okay.
So instead of just squaring, let's do like taking the n power, okay?
Okay.
So okay, here I'm gonna use some identity which is called Newton binomial identity.
Uh-huh.
You know what I want? I want.
Isn't this the binomial theorem?
Yeah. It is exactly that.
Oh.
Okay. But then, okay, then it looks very complicated, but it's not actually, because we have the equation xy is equal to 0, so almost all terms are 0, right?
Yeah.
So what we will be left with is, maybe let's see if I'm able to write the coefficient. So we're gonna get n0 choose 0, an, plus, so what's gonna be the other guy is gonna be n1 with an minus 1 x exposed on 1, right? But there's no other case, there is no longer any, there's no term after that, because we have x squared is equal to 0, right?
Right.
Therefore we only have those, and n choose 0 is just 1, so we just get an, and the other guy is n choose 1, which is n. Okay. And now do you see like some kind of pattern going on here?
Yeah.
So what is the thing on the right?
It's practically reminds me of derivative.
It is. It is the derivative of your function.
Oh, okay.
That's kind of cool. So in general, if you have a polynomial function, what it will do is, if you evaluate to a plus x, it will compute you f of a plus f prime of a times x.
Okay. So isn't that like a I don't want to say the wrong terms, but is it like a Taylor series or a power series?
Sort of. It kind of drops the. It kind of, but it's a Taylor series, but we sort of drop after degree 2, right?
Right. Yeah.
So
does that mean we can actually create? I guess what you're trying to show me is it like the mind-blowing thing is that can we make like derivatives like considered like a field, or like at least this type of
those wouldn't be field, but those are just like kind of an interesting example to look at.
Oh, okay.
I mean, in algebraic geometry, we sometimes use the ring that we just created as a way to define derivative.
Oh, okay.
And for example, there is also application. I mean, I've seen people talk about application in machine learning. So in machine learning, you have like so basically you usually have a loss function, which is something you want to minimize. Okay.
Okay.
And usually it's kind of like the process is kind of similar with what you did in maybe first calculus or maybe multivariate calculus. You want to compute the gradient, i.e. the derivative if you involve variable. Okay. And then you sort of want to use the derivative to tell you where the minima is. You know, in calculus you would look where is the derivative is 0. Well, you cannot exactly do that with a neural network, but you can at least use it to give you some direction on where the minima should be. But the problem is that neural networks are very deep. So basically a neural network is, you can sort of think of them as a composition of multiple functions, right?
Okay.
Right. And what's gonna happen if you try to compute the gradients, you're gonna have the chain rules that's gonna apply.
Alright.
Right? And if you're like in one variable, what the chain rule is doing like something very bad, right?
Yeah.
It's sort of giving you like a lot of product, right? So if you do a lot of composition, you just end up with a very long product.
Yeah.
And as neural network can be very deep, this product can be very long. And if you start, maybe like you're like, oh, I guess we're computing on a computer, so maybe we don't really care about the exact value of the derivative. So maybe it does not matter. But as you're multiplying like for example, if you're multiplying so many like small number, you can get the problem with the stability of the computation. You just get the wrong answer because you did too much multiplication with very small number or very big number. So usually in like if you look at what is the word, PyTorch, which I don't know if it's still a very popular framework for machine learning, but it was at some point. They don't compute the derivative in the numerical way. What they do is they do like a graph of all their function, and they're using those kind of numbers to compute their derivative for them. And this is like what they use, for example, computing the gradient for a big neural network and stuff like that. So,
okay.
It's kind of a niche application, but it's kind of cool at the same time. But usually in algebraic geometry, we use them to define the derivative, or we can use it to find what we call fat point.
Okay. So
those are a bit, but those are a bit. Those are a bit more complicated.
It sounds complicated.
Yeah. So next time, we're gonna finish the construction of the real number, and what we're gonna show. So we know that the Cauchy sequence itself the set of Cauchy sequence form a ring. And now what we're gonna do is, we want the real number to be a field, right? So from the construction we saw today, we just need to find some specific ideal which is gonna be maximal and give us the property we want. And for us, the field will be the ideal will be the following. It will be all the Cauchy sequence that converge to 0.
Okay.
And so next time, what we're gonna do is we're gonna show that this is an ideal.
So what you wrote, like underneath AN, is like all sequences converge to 0, right?
Yeah.
Okay.
So we're gonna consider the set of all sequences that converge to 0. So this is an ideal, and in fact, maximal. And so basically, what we're gonna get from the theory that we did today is that therefore R is gonna be a field.
Okay. So we'll use an ideal and the minimal fact to show that the real numbers is a field.
Yeah, so we're gonna use the fact it's maximal to conclude that R is a field. So it's going to be one application of the theory that we introduced today for next time.
Oh, okay. So this is like a precursor to like basically introduce what the real numbers are, right? For like the next time, right?
Yeah.
Okay.
Yeah. So here I was kind of explaining why. I mean, first of all, we were talking about constructing the real number, and why on earth we went to ring theory to do that. And the reason why is because from the quotient construction we can get for free that R is a field.
Yeah.
And also I wanted to show you that we can build how we can build field using polynomials, and you sort of saw how we can build a complex number from that.
Yeah. I'll definitely probably rewatch this video like over.
Yeah,
and over.
Maybe I went a little bit too fast today. I mean, I kind of underestimate the time it's gonna take.
Our chat was like our chat is pretty smart. So like, I think some of them even said that you were probably going too slow for them, I guess. So you know,
maybe.
maybe but you went in a moderate pace for me. So
Yeah, I mean, yeah, I kind of don't want to do like the entire. Okay, that's the important part.
Yeah. Okay. Well, thank you again, Sasha, for like an awesome, informative lecture as always, and also like special thanks to you for like offering to like teach me like all this stuff, because I know it's like a lot of your time and a lot of your effort to like actually put not only this but the assignments together. Like, I'm always grateful to you, my friend.
Yeah.
Do you have anything to say to our global audience before we end stream today?
Well, drop the bell, drop the drop the like, drop the sub, go on the Discord channel. What am I missing?
Yeah, I'll put those in the chat right now. So, Tube and our Discord server. And if you want to check out my video game content, you can also check out my Uncle Talks channel. They're all there in the chat, and also if you're watching this on YouTube, all the links will be in the description down below. Yeah, I always appreciate you guys like coming in, and if you guys basically need like a productive stream to keep yourselves like productive, like you can always pop in. If you love math and physics, like you can drop in, and basically we can like talk some stuff, exchange knowledge together and all that stuff, so we can become much better I guess like people that love both math and physics. I will say that for sure. I don't want to say scholars, because obviously like we're not in academia. at least like I'm not. So I mean, if you all are in like grad school or nothing or something, then I congratulate you for actually being in that. Sascha is one of them, and I'm always rooting for him to basically get to his next field of study, whichever it may lead him to.
Who was in the chat?
What's up?
So who was in the chat? Oh, it was Storm. Yeah, I guess Storm already did all of those stuff, so probably it was a little bit too easy for him.
Yeah.
But at the end, it's important for you to understand. So,
but
like if you have questions, don't be shy to ask.
Yeah, like because like basically like
gladly help you.
Yeah, like I just want to like basically say something, because I think someone said something in the chat, and it so basically like I am a math hobbyist, I'm a physics hobbyist. I am not someone who's like going to grad school or anything. I just love the subjects, and like if you're coming into my channel thinking that I'm going to teach you something like extraordinary, I apologize for disappointing you. I'm just learning these subjects as much as like anyone who just loves the subjects. So I am not a scholar, I am not a professor or anything. I'm just someone that just loves the subjects, and Sascha is just the awesome scholar that is willing to teach me his ultimate wisdom. That's all I'm saying.
Yeah.
Alright, so let's see if there's anyone we can raid for Twitch, because we haven't done that many raids for our... And
I think you have Academia of Useless ID, which is online.
Yeah, I'll definitely give him a raid. Because if you're a math hobbyist, or you're already in undergrad, like we're all rooting for you in this community. Because I know Sascha wants you to succeed, and I want you to succeed. So I guess we'll do a raid in the Academy of Useless Ideas. Now he introduces a lot of math that goes over my head, but at the same time, it's like I'm willing to actually like learn like the terminology and everything. So we'll do the raid message for you guys. And Sascha and me will basically return tomorrow for another awesome lecture about the real numbers. And after that, Sascha, what would happen the next week? What do you plan for the next week after we cover tomorrow's lesson?
So I guess we could start like doing linear algebra, and like one day will be a linear algebra and the other will be a real analysis, and maybe the third day could be like an exercise day or something.
Oh, okay. Yeah, so like
Like,
putting all the knowledge that you gave me into practice.
yeah, because right now I feel like I'm kind of dumping you a lot of math on you, so you
No,
have to
it's fine.
you have to
Yeah,
do some
like
exercise
yeah,
to
yeah,
assimilate.
yeah. I probably will do the exercises that you assigned us, and that way I'll struggle throughout the stream. Okay, guys, we're gonna commence
Yeah.
the raid, and always remember, everyone is precious. You guys are just as precious as everyone else, and we will see you guys in Academy stream. So take care, guys. Bye bye.